Hi, this is ET 350 Lecture 13. Today what we're going to do is a review of AC power. We'll look at a simulation, just try to bring up all the fundamentals that we may have forgotten in the past year. We're also going to look at this concept called impedance transformation. We'll see how it kind of relates to a dynamics example. And then we'll look at equivalent inertias or impedance. And so these are the formulas. And so what you have is if you have a transformer and you're bringing an impedance like a resistor, inductor, or capacitor, and you're trying to equivalently represent it across a transformation or a transformer, you have this kind of square thing. It's not just a straight up ND over NS, and you'll see why later. Same for a similar to a source transformation, but in source transformation, you actually just follow your similar ideal transformer relationship rules. So there is going to be no square. And lastly, we'll look at an example in simulation. Hopefully it'll hit both of this and your review of AC power home. Okay, so let's begin. So let's just look at a simple element. Could be anything. This could be a resistor, capacitor, inductor combinations, right? And you have some voltage and some current. And note for this example, we're showing that the current enters the positive terminal of the voltage. Just makes things simpler because then we use the positive IV version, right? It still works if we had it the other way, but let's just keep it like this. All right. Now, if we're talking about AC, we have the current and voltage as these cosines, right? IP cosine of omega t plus theta I, VP cosine of omega t plus theta V, okay? And when we multiply these two things together, we get the instantaneous power and from the perspective of power absorbed, okay? So let's review what are these little terms again. Amplitude, IP and VP, the angular frequency, so this is related to like the 60 hertz. So if it's 60 hertz, then you got to multiply it by 2 pi to convert it to radians. This is radians per second. And then theta I and theta V are the phase shift, if you recall. So this is the vertical stretch, this is the horizontal stretch, and this is the horizontal sliding, right? And so if you have something leading, something is sliding to the left earlier in time. If you have something lagging, right, a more smaller number, then it's shifting to the right, okay? So this is the way to write it as a phasor. Don't forget the difference between RMS and peak. You can write these both either as their peak or RMS, and the factor is √2. The RMS equals the peak over √2, square root of 2. Okay, so hopefully this is all a nice review of ET250. Okay, now, another thing to remember when you write it as phasor form, you are assuming that the angular frequency is constant. You're kind of ignoring the angular frequency when you write it as phasor form. So that's a free variable, okay? All right, we also have the power triangle. We had this P, Q, theta, and S. And you're like, wait, what was that again? All right, well, S is the complex power phasor. This is, or S bar is the complex power. S is the apparent power, okay? We quote this in units of volt amps. Theta is the phase of the power phasor, and it's defined as theta V minus theta I. So it's the phase of the voltage minus the phase of the current. And by the way, just as a note, this is the same as theta Z if this was an impedance, okay? This doesn't have to be an impedance, but if it is, it's theta V. Theta V minus theta I is theta Z. All right, what's P? P is the real power, or it's the average of the instantaneous power. And what's the instantaneous power? It's the multiplication of these two. And so if you recall from 250, if these are sinusoids going up and down, the instantaneous power will also be sinusoidal at twice the frequency of this, because there's going to be twice as many 0 points. Okay, so you have your real power, which is the average of this, and then you have Q. And Q is what we call the reactive power. We use watts and bars, right, for the distinguishing these two. And if you recall from ET250, Q is the amplitude of the component of the instantaneous power here that bounces back and forth, okay? So let's say you have something where this S is totally on the y-axis. Well, all the instantaneous power is bouncing back and forth in that case, and Q would be the amplitude of that, okay? If this thing is now only on the x-axis, that means Q is 0. There's no power that bounces back and forth, and the all the average power is P. Okay. Now it doesn't mean the instantaneous power doesn't oscillate, but it does mean that it's all positive or all negative. Okay. All right. Now here's some other familiar equations. If you want to calculate P, it's IRMS VRMS, which is just S times the cosine of theta V minus theta I. Okay, so theta is theta V minus theta I. And you can easily see this from trig. S is, of course, IRMS VRMS. It's like the total available power. Notice cosine can be anywhere between -1 and 1. But S is like the absolute maximum power you could achieve. It's like your potential. The power factor is this. It's the ratio of P and S, right? If the power factor is 1, what happens? S and P are equal, okay? And we can also have an expression for Q. It's IRMS VRMS times the sine of theta V minus theta I. Okay, so these are the easy formulas that you can remember, that you should have memorized to be able to calculate all these quantities. The last thing that I wanted to review was the equations for power and real power, or the average of the instantaneous power in Q. And this is assuming that this is a Z in impedance, a resistor, inductor, capacitor, some combination of the three. And so we have IRMS squared times the real part of Z. So if Z is a complex number, remember we have real and imaginary, it's the real part. Or the alternate formula is VRMS squared, real part of Z over the magnitude of Z squared. Remember, the magnitude is just like, you know, if you have a phasor, it would be like the length of the phasor. The real part is like the X component, and the imaginary component is the Y component. Now, it's very similar for Q. It's IRMS squared times the imaginary part of Z, and VRMS squared times the imaginary part of Z over Z squared. So if you remember one, you can remember the other. So these, you know, these are just useful formulas in case your element that you're looking for is a Z. It's like a resistor. Remember the DC case, I squared R, V squared over R, right? Look how the formulas are matched, right? Okay. Let's look at a simulation and see that this has some consistency. Okay, so let's switch over to the computer. And so I'm going to share my screen. Okay, so I set up 3 circuits here. And so let's just look at the left one. The left one is an AC voltage supply. So let's say 120 volts max, okay, 60 hertz, right? And I have a pure resistor. I'm measuring the voltage and current, and it's showing up in this plot down here on the lower left, okay? So what we see here is that the voltage and current are actually in sync. Notice that the current and voltage, they're in phase, right? I'm monitoring the power here of the source, and you can see it's all negative, which means it is constantly delivering power, and that makes sense. It doesn't matter which way the currents are flowing, if this power source is always delivering power, always negative, okay? Look at the yellow current and the green voltage, green and red voltage. So when it's green, the current goes forward. When it's red, the current goes back. There's no lag, there's no lead in the current relative to the voltage. And so you have everything in phase. The power factor in this case would be 1. All the apparent power is equal to the real power, okay? And so your power triangle for this guy here would be a horizontal line, okay? So hopefully this makes sense. Notice that the instantaneous power is still oscillatory, and it is 2 times the frequency of either the current or voltage, all right? So here is an AC power situation, single phase with just a resistor. Okay, so I'm going to turn this off so it's not as distracting. I'm going to go over here and let's look at the capacitor. Now, if you remember, a capacitor and a resistor is going to have a leading current. So I have the current monitored and the voltage. So the current will lead the voltage in time. And so let's see that that's true. Okay. See how the yellow current leads the green voltage in time? It comes before in time. Okay. And notice, again, I'm plotting the power of the source here. And so the power of the source, notice it doesn't perfectly oscillate it all negative. It has a little bit of positive parts, okay? A little bit of positive parts. That tells us that there's a non-zero Q, right? There's some component of this that bounces back and forth. The average is negative 15 here. So it is still delivering power in the average, but there are some points in the cycle where it actually gets some power back. All right. Still, the power is also instantaneous power is oscillating, and but the average is now a little bit shifted up. Okay. All right. So let's and then again, last thing is you can look at the yellow balls that are moving, and then the voltages, and you can see that the current leads the voltage. So the yellow starts moving and then it changes color. So the yellow starts moving and then it changes color. So the current is leading the voltage. And this is all coming from this spring-like capacitance effect, because this is acting like a spring, okay? Resistors are acting like dampers. Okay, so let's do this. And now let's go to the last one. The last one is an inductive element. And if you recall, the water wheel effect, that's going to create a lagging type of situation where the current lags the voltage, okay? And so when we ping this in, we see the current lagging. Look at the yellow line lag behind the green voltage, right? And you can see that the color of the voltage changes and then the current follows, right? So we have a current lagging the voltage. Again, we can see that the instantaneous power is still oscillating. Yes, this power supply is delivering power in the average because it is negative, but we notice that it's not perfectly all negative at all times, okay? Now, let's say we were to decrease this resistor. If we were to decrease this resistor, it becomes more inductive, right? This entire load becomes more inductive, which means that the current and the voltage will become more and more out of phase. Theta V minus theta I will get closer and closer to 90 degrees. On your power triangle, what does that mean? That means your power triangle is going to point more and more vertical, okay? There's going to be less and less P. And so what we should see if I decrease this resistor is that the current yellow will lag more. Okay, the peak will center over the 0 point of the voltage, and this instantaneous power curve will rise up. Okay, and it'll oscillate about 0, which means the average would be closer to 0 watts. But then the Q dominates, and what is Q? The amplitude of the component of the instantaneous power that bounces back and forth. Okay, so let's do that. Let's bring this down to 12, let's say, and see what happens. Okay, and you can see, look at the yellow. The yellow current now lags by the green voltage by nearly 90 degrees. And look at the instantaneous power. Look how after it settles out, it starts oscillating nearly about 0 watts, right? And so you can see that the wattage in the average definitely decreased from before, okay? We still have some resistance, so that it's not a non-zero, so you still have 9 watts burning off in this 12 ohm resistor, but notice how it shifted up. So the P now is very small, and I would say the power triangle is looking close to vertical with a slight angle forward, okay? All right, so I hope this was a good review. Please rewind and rewatch this video. I'll have the link to this simulation in the description, so you can check it out, play with this on your own. But I hope this review of the AC circuits was very useful. Okay, let's go back to the document. All right, so let's talk about this new concept called impedance transformation. All right, and so the idea is, let's say you have a transformer here. And the question is, well, if I had some primary voltage source, how would this Z feel as if I were to pull it across the transformer, right? Right now, it's a little bit kind of unintuitive to have a feeling for what Z is with this N1, N2 in the way, right? And so what would be the equivalent circuit of bringing this Z over here? We'll call it, let's say, Z prime. We want these both, let's say, to be equivalent. What was equivalent again? Same power draw under the same condition, right? And so the question is there a Z prime that feels the same as the Z behind the N1 and N2 of the transformer? That's the concept of this impedance transformation. Kind of like a Thevenin Norton equivalent from ET250, right? What is the Thevenin equivalent, Norton equivalent of this brought over? Okay, so that's the whole idea right now of this discussion on impedance transformation. Okay, now before we dive into the electrical version, I want to do the same thing for a mechanical system, because I feel like A mechanical system, we can get the intuition faster, and then once we apply it to the electrical, it'll make hopefully a little more sense. Okay, so what that's the same reason why we bring up the hydro analogies. But let's look at a mechanical system. Let's say we have a flywheel, and what does a flywheel have? It has inertia. You can apply some torque to it, and what do you get when you apply torque? You get some angular velocity and angular acceleration by omega and alpha. We know in a linear sense, F equals ma, no problem. That's the Ohm's law of dynamics. And in a rotational sense, torque equals I alpha. Again, the Ohm's law of dynamics in the rotational sense, okay? These are the units, right? Just a good review: Newton meters, kilogram meter squared, radians per second squared. This should all cancel to be Newton meters, good. So just a review of the theory of dynamics, okay? And then in this case, I is kind of acting like the impedance. It's like an L or a capacitor or a resistor, okay? And more I here, if this is a bigger diameter flywheel, it'll be harder and harder to accelerate, okay? Just like you have a bigger resistor or inductor, it's harder and harder to get current to flow through. Okay, so let's dive deeper. Let's look at a more complicated mechanical system like a bicycle. All right, so let's say you are the human and you have an N1 and N2, kind of like a transformer, N1, N2. You have your input torque, torque 1, omega 1, alpha 1, and you have some output torque, torque 2, omega 2, alpha 2, okay? So these things are obviously coupled by the gear ratio, right? You got your front gear, your derailleur, and your rear cassette, okay? And you have some inertia. Let's say your wheel is the inertia, okay? Now the question is there an I in terms of N1, N2, and I2 such that this system behaves like this, like a simple flywheel, right? Can we do this? Okay, so let's see if we can transform this I2 to the other side, just like we want to do with the electrical system. Okay, all right, so let's go back to your torque 2, I2, alpha 2. Yep, that makes sense. That's the Ohm's law or the dynamics Ohm's law. Torque 1, I, which we don't know yet, we want to find alpha 1. Okay, is there I that behaves like this? So let's assume we have an ideal transformer, right? Or I'm getting mixed now. Gear ratio. So we know torque 2 equals N2 over N1 torque 1. Okay, and recall your gear ratio lecture. So omega 2 is the opposite, N1 over N2 omega 1. Take a derivative of this and you get alpha 2 equals N1 over N2 alpha 1. Okay, good. These are all just mechanical gear ratio properties that we should know and love. Okay, if it's ideal, the power is conserved. Okay, and so let's see what we get if we divide torque 2 by alpha 2. Well, torque 2 divided by alpha 2, what do we get? We get actually I2, that's nice. Okay, well, what else is torque 2 over alpha 2? Well, look at this. So we have two expressions for torque 2. We have this and we have this. So we can put it in, N2 over N1 torque 1, good. And for alpha 2, we have this, N1 over N2 alpha 1. Okay, so this is nice. This shows us a relationship between I and look, torque 1 and alpha 1. If I solve for torque 1 and alpha 1, what do I get? I'm going to get this. I'm going to get this I is going to be the same as N1 squared over N2 squared I2. Interesting, right? So if I replace this torque 1 alpha 1 with the unknown I, right? Well, if I solve for this I and I bring these guys over here, I get N1 squared over N2 squared I2 equals that I. And so what does that mean? Let's try to get intuitive feeling for this equation. What it's saying is, if I want to replace this system such that I have kind of this system, so it's like bringing this I2 over, all I have to do is multiply it by the square of the ratio, okay? And notice the n squared, and the squared is important, okay? Let's put some numbers on it just to make sure we again get some sense. So let's say we have N1, N2, this is 10 to 1, 10 to 1, or sorry, 10 to 1. So this is 10 turns and 100 turns, okay? And so let's say the wheel is a 2 kilogram meter squared inertia, okay? All right, So from the perspective of the rider, if we take this formula here, what do we get? 10 squared over 100 squared. So even though the ratio is 1 to 10, the amplification here, or the de-amplification, I should say, is 1/100, right? Because we get 1/100. So what does that mean? That means that this inertia with this 10 to 1 gear ratio is going to feel 100 times lighter because you have the gear ratio. And that should make sense. This gear ratio is helping the rider, right? It's making this eye feel easier, all right? So that's what this is doing, okay? So, and it's not just the N1 over N2, it's the N1 squared over N2 squared, all right? So the wheel feels a lot lighter, okay? And what does that mean? Easier to accelerate, right? Due to the gears. Okay, so now let's go back to the electrical system and see if we see the same kind of correspondence. N1, N2, Z, and it's the same thing. The Z prime is the N1 squared over N2 squared Z. And so the pattern is, let's say I have the Z at a start, and the N on the start side and the N on the destination side. If I want to bring the Z on the start side over to the destination side, then the Z at the destination side is N destination squared over N start squared over Z times Z start, same as the mechanical. So we can remember this as an equation. Okay, good. All right, so here, notice we don't care, there's no sign change, dot convention. So if you had a plus or minus or dots, if you're just moving Z's over, you don't care about the sign. And that should make sense. The Z shouldn't be affected by this sign, okay? And because impedance is passive, we don't care, okay? All right, now what about if you wanna look at the individual resistors and capacitors and inductors? How do those, so this is the Z, this is the overall impedance, right? But what is the Z made of? R's and L's and C's, okay? So how do those get affected? Well, if I have a resistor, I know that ZD equals ND squared over NS squared ZS. And if I had some resistor at the start, how would I represent it as a new resistor? Well, I could replace this Z with an R, Z with an R, and then apply the same formula. Oh, it's the same formula, no problem. ND squared over NS squared R. Okay, what about an inductor? Okay, same situation, except I have an L instead of an R. I could apply the formula that we just wrote, okay? And what's the Z for an inductor? J omega L, don't forget that, okay? Look at the J and omegas, they cancel. Again, I have the same formula, yay. Resistor is nice, it just follows the Z equation. Inductor is nice, it just follows the Z equation. What if we had a capacitor? Of course, there's always going to be something tricky with a capacitor, okay? So we have, again, same formula, here, here, and here. But now let's look at the capacitor. We got to put a 1 over J, 1 over JC, 1 over JCD, right? That's going to mess things up a little bit, okay? And because of that, look at this. The C at the destination, so if I want to bring a capacitor over, the equivalent C here is actually NS squared over ND squared. It flips the ratio. But this is how you would bring a capacitor over. You just have to invert it. So be careful of that, okay? Switch of the pattern, be careful. Okay, very good. So what about sources? What if I had a source on one side and I wanted to bring it over? Well, that's nice. You just use your normal source transformation, your ideal transformer relationship. V destination equals plus or minus N destination over N source Vs. It's the same as these ones, V2 equals N2 over N1 V1. Same with here. And how do you determine the sign? It's still the dot convention. Okay, so all this will be highlighted in the next example. All right, let's keep going. Okay, so let's look at this simple example. So what do we have here? We have a voltage source with 10 volts peak at 0 phase. We have a transformer with the dots on the diagonal, V1, V2, I1, and I2 labeled, nice. And we have a Z here of 3 ohms at a 30-degree phase. That means the theta V minus theta I of this guy is 30. And NA is 3 and 6, so NB is 6. This is like a 1 to 2, right? So you get an amplification of voltage at V2 relative to that V or V1. KVL, look at this. V1 and V are the same. Okay, V2 is across Z. Okay, we're all good. Okay, so what we're going to do is we're going to transform the Z to the left side, right? We're going to do that Z transformation and see and compute the power over this new Z prime. And then we're going to do the same thing is we're going to keep Z and then transform V over to the right side, and we're going to get a V prime. And what we're going to do is also calculate the power. And what I want to do is I want to see equivalence. I want to see when I take the Z, bring it over to the left, and calculate the power of Z prime, the power I get here is the same as if I were to bring this V over, get a V prime, and calculate the power for just Z by itself. Let's go. So these are the two systems, just to see what we have. Z brings O across the transformer, I get a Z prime, V stays the same. And this V goes across the transformer, V prime, get Z. Both of these should be behaving in a similar fashion in that they're both dissipating the same amount of power in their Z's, okay? Okay, so let's look at the first one, this one over here on the left. If I want to bring this Z over, I can use my new impedance transformation rule. And in this case, Z prime is the destination, good. Z is the source, good. NA is the destination, and NB is the source. Not too bad. I have all those numbers. Easy, 3 squared, 6 squared, 3 angle 30. Notice it only affects the magnitude. 3 over 6 is 1/2. 1/2 squared is 1/4. So this Z becomes a quarter lighter, right? And a quarter easier, less impedance. So it's 0.75 instead of 3. So from V's perspective, Z gets smaller by 1/4. We can use our reviewed power equations. What do we have? V RMS squared real of Z prime over the magnitude of Z squared. Okay, so what's the real part? What's the RMS? What's the magnitude? Well, the RMS is peak over root 2. And so this V, it's 10 over root 2, nice. What's the real part of Z prime? Well, if you remember, it's the length times the cosine of the angle, okay? Length times the cosine of the angle, which is 0.75 cosine 30. And what's the magnitude of Z squared? Well, the magnitude is just this guy, easy to read off, 0.75 squared. If you were given the Cartesian coordinates, then what would you have to do? You would have to do the real squared plus the imaginary squared square root to get the magnitude, okay? And so we get 57.73 watts, all right, not too bad. Let's do the second one. So the second one is we're gonna bring the source over, so we have this, and then we're gonna calculate the power for this. So what do we have? We have the destination, which is bringing this over equals plus or minus n destination over NSDS. Okay, in this case, the destination is the B side, not the A side, and the source is the A side, and then this V is the same as V1 by KVL. Okay, we still have the dot convention. Look at this, because V and V1 are the same, and V2, we have the minus touching the positive touching, we have to put a negative. Good. So that's not too bad, just punch in the numbers, 6, 3, 10, good. And so I get a multiplication of 2, not 2 squared. Notice in the source transformation, there's no squared, only in the impedance transformation. So I get negative 20 angle 0. That's equivalent, by the way, as 20, positive 20 angle 180, right? So those are the same things, just a bit of trivia. And so from Z's perspective, if I move this V over, V prime is bigger, and that should make sense. This transformer is magnifying that V, okay? So if I want to calculate the power again, I can now use V prime squared, the new V prime over here squared, times the real part of Z, not Z prime, because we're analyzing this side, over magnitude of V squared, okay? So again, this is RMS is peak over root 2, so it's 20 in this case over root 2 squared. The Z is this original one, so the real part is 3 cosine 30, and the magnitude is just the 3 by itself, so 3 squared. And again, we get, if you punch these both in your calculator, 57.73 watts. So that's nice. We get the same as case 1, so they are consistent, right? So if we wanted to bring this over or bring that over, we get the same power. So what I did is I wanted to put this in a simulation and see if we're getting similar results here. Okay, and so in the simulation, I can't just put a Z of 3 angle 30. I actually have to pick a R and an L and a C. And so it's like, oh, what's the resistor and inductor or capacitor that I should have picked? Okay, well, what do we see here? 30 degrees is theta V minus theta I. If theta V minus theta I is a positive number, then we know it's an inductive type of situation, right? Because the I is lagging the V, and that's what inductor does, the flywheel effect, right? Okay, So if that's the case, we could pick a resistor and inductor in series for the Z. And now, based on this information, we could come up with the R and L to make 3 angle 30. And now the reason I bring this up, this is a good review. So Z equivalent, right, because it's in series is going to be ZR plus ZL, which is R plus J omega L, okay? We want the magnitude of Z to be 3, and we want the angle of Z, which we'll call theta, to be 30. Okay, no problem with that. With Pythagorean theorem, we can say R squared plus omega L squared equals 3 squared. Good. And we know from the tangent of 30, or tangent of theta, is the imaginary part, which is omega L over R. Okay. If we assume, look at this, we have 2 equations and 3 unknowns, but if we assume an omega, let's say, you know, omega is 2 pi f, f is 60 hertz. Let's say we assume omega, which is about around 360 radians per second. We actually have 2 equations, 2 unknowns. We could solve for L and R. And so I've done that, and I actually get 2.59 for R and 3.97 millihenries for L. So a little baby inductor and a resistor. And do those numbers kind of make sense? Yeah, that seems to make sense. I have something maybe on the imaginary axis that looks kind of like this, I would say, where the length is 3, yeah, 30 degrees, 2.59, yeah, L, yeah, okay. That makes sense. Okay, yeah. So this is your phasor plot. Okay. So let's go over the simulation with these numbers punched in and see if we're getting that 57 watts. All right. So we're going to share screen. Go back to the simulation. Okay, so now we're in the simulation again, and now I have the problem modeled. Okay, so check this out. The top one, I have a transformer. I have the original 10 volts peak, the cross dots, and I have the 2.59 ohms, and I have the 3.97 millihenries. Okay, and what do I have here is I have the power supply plotted, right, in this lower left plot. And it's a little bit wonky because the transformer does add a little weirdness. I have a 2-to-1 ratio, 3 to 6. I had to tweak this primary inductance, but when I tweaked it, I did get an ideal relationship going through, and I get about 57 watts dissipating out of this voltage source, dumping into this resistor and inductor combination. Nice. So then I went, okay, let's do the first case where I brought the Z over to the left. And if you remember, that actually is nice for resistor and inductor. I just used the NA squared over NB squared times the Z, which in our case ended up being 1/4 because this was a 3/6, right? Or 1/2, right? So this is the 1/2 squared, which is 1/4. So these are the quarter of these values. And if you notice, I plot these in the middle plot here. Okay, so this is the middle plot. If you look at the average, I get, again, negative 57 watts, okay? And the good thing is you're seeing that I am monitoring to this current voltage. You're seeing a delay in the current, right? A lag in the current, inductive, right? In all cases, you're seeing inductive. Okay, on the right side, what we have here is the same impedance. So the Z and the Z match, but now I brought the voltage source over. So instead of 10, I've amplified to 20 volts peak, because I use the source transformation, NB over NA, no squared. And again, if I plot the power of this source, look at this. Again, negative 57 watts on average, all right? So I'm getting the equivalent power draw on all these equivalent circuits. So this is the original circuit. This left one, lower left, is bringing the Z over on this side. This lower right is bringing the V over on the right side, okay? I hope this lecture and these examples helped, and I'll see you in class. Have a great day.